Hey, this is Juan Berciaga doing a standard on beats. But before we get to beats, I kind of want to use the analogy on cars racing around a track to compare it to beats later on. So we have this racetrack here, and then we have two cars. Let's say that the blue car is faster than the green car, so this one would be slow. And then if we knew the difference of the speed of both cars, it wouldn't make a difference. We would be able to find how long it would take to go around the track, but we don't know that. But we can say that the speed of the fast car does not equal the speed of the slow car, so this would be creating lapping. So the fast car will be passing at a certain point the slow car. So we can say that lapping happens every 2 minutes. So for that to happen, we want to know how much faster is the fast car compared to the slow car. So we equal to each other. So we know that the fast car equals the speed of the slow car plus the additional speed because the fast car apparently is faster. We assume that the track or one time around is 3 miles. If we knew the speed of both of the cars, we would figure out how long it would take to get around, but we don't know that. So we can put them into their own little equation. So if the slow car here goes x number of times around in 2 minutes, the fast car would be x plus 1, so it would be the speed of the slow car, which is x times around in 2 minutes, plus the additional speed, so 1. You're going to go one time around faster than the slow car. We can create little equations here. We have two cars and create two equations. X equals the slow car times 2 minutes. And we could also do the x plus 1 equals the speed of the fast car times 2 minutes, which is a whole lap that it goes around because of lapping again. And we would like to find the difference of the second equation minus the first equation. So we would get, if we put them all together, x plus 1, which is the fast car, minus x, which is the slow car, and we apparently get 1. And then we can go into further depth to saying that it equals 2 minutes times the speed of the fast car minus the speed of the slow car. So we would get the speed of the fast, to find this, we would get the speed of the fast car minus slow car, which would be 3 miles around. That's how long the track is, divided by 2 for every lapping. These 3 miles identify how far around. So when we divide that, we get 1.5 miles per minute. Times that by 60 to turn them into hours, we get 90 miles per hour. If we want to compare this to beats, we would like to do the track around. We would turn that into 1. We'll talk about that later. So we can do 3 divided by 1, which is 3. So we get 3 miles per minute. Times that by 60 is 180 miles per hour, would be the difference of the speed. And then comparing this to beats, we have the analogy of the car and compare it to sound. Speed equals the frequency. The speed difference is the frequency difference in sound, and the lapping time is beats or pulsing spacing, and then the change in speed equals the track divided by time. That's what we found in this equation. So we'll go back on this one, and in sound the change of frequency is 1 over beat. That's why we changed the track to 1 in the second equation. So if you hear 4 times, sound 4 times per second, F2 equals F1, the difference will be plus or minus 4 hertz. That would be the change in frequency. So the reason why it's plus or minus is because we don't know which one's higher between the first frequency or the second frequency. We can just always say we add 4 or subtract 4 to find the difference. The first frequency or the second frequency, they sometimes swap roles. That's why we add or subtract once again. We could also compare this to tuning. When you're changing the tension or extending on a trombone, you want to find that perfect tuning. So if it was 4 hertz, it would sound like wah 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 wah. You can hear the beat pulse. So if you were tuning, was say a guitar, you want to find that perfect tuning where they equal each other. So when you're tuning it, it would try to get it into sync. First it would be like wah 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 wah, and then when it's synced, it'll be like wah 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 wah. That's when you know it's in sync. And that's all I got. Thank you for your time.